This is part 2 of solving equivalent series parallel circuits. So this question says, find the equivalent resistance RAB in the circuit, right? So this is our circuit. Now when we look at this, we might get really confused, right? We have a lot of slanted lines and, this might kind of throw us off. So what I first would like to do is, if I have a slanted line like this, from one diagonal to the next, I like to draw it as a horizontal line, right? So I'm just going to redraw this circuit to look something like this. This is going to be 6 kilo ohm. This resistor is going to be 5K. So because this is a slanted resistor, I'm just going to draw it as a vertical line. We know that's going to be 3K. Then we have this vertical resistor. So I'm just going to draw it back as a vertical resistor. And that's 3K. Then we have this slanted resistor once again. So I'm also going to draw this as a vertical wire. This is going to be 4K. And finally, we have this 4K resistor with this 8K resistor. So I'm going to have a 4 kilo ohm resistor in series with this 8 kilo ohm resistor. And because there's no resistors at the bottom of this wire, we can just finish connecting these wires together. Okay, now that we have this, we can start to simplify this, right? So we know we're going to be looking through these terminals. And we want to find the equivalent resistance. So we're going to start at this location right here. We know this 4K is in series with this 8K resistor. Therefore, we can just add these two, right? Because resistors in series, we can just add. 4 plus 8 is going to give us 12. So when I redraw all of this now, I can just redraw it to look like this. And we know we got this 12 by saying 4 plus 8, right? Now when we look at this, let me just circle it. So we had 4 and 8. Now when we look at this, we can see that these two resistors are going to be in parallel, right? But when we take a good look at this, we have these two resistors in parallel, but we know that this is also in parallel with these two resistors, and this resistor is also in parallel. So in this particular circuit, we have 4 resistors that are actually in parallel. So why don't we just find the equivalent resistance for all 4 of these resistors to save us time? So when we find the equivalent resistance for all of these resistors, we're going to say that's going to give us 1 over Req, which equals 1 over 3, plus 1 over 3, plus 1 over 4, plus 1 over 12. When you solve for this, that's going to give you 1. Therefore, Req is going to equal 1 kilo ohm. So let's redraw this circuit now. When we redraw this circuit, it's going to look something like this. This is going to be A. This is going to be B. Going to have 5 kilo ohm. And we know we just combined all of those resistors, which was this 3K, this 3K, this 4K, this 12K. And that's going to give us 1 kilo ohm. So we have a 6K here. We have a 5K here. And finally, we have a 1K here. Now, when we look at this, we can see that these two resistors are going to be in series. So when we add this, we can say 5 plus 1. It's going to give us 6 kilo ohm. Let's redraw this. We're going to have this 6 kilo ohm here. And that's going to be parallel to this 6 kilo ohm here. Right? So these two resistors are in parallel. Do not think these are in series, right? Sometimes that can trip me up. Remember, right? Think of it like this. This is the positive terminal. This is the negative terminal. We have current we have current flowing from the positive terminal going this way. Once it reaches to this node, that current is now going to split. It's going to go in this direction and it's going to go in this direction, which means these two resistors are going to be in parallel, not series. So when we find the equivalent resistance of these two resistors, we're going to get 6 times 6 over 6 plus 6. That's going to give us 3 kilo ohm. So when we draw the circuit for our final time, we're going to get the circuit that looks like this. 3 kilo ohm. So our answer for this particular problem is going to be 3 kilo ohm. So that's how you solve problems like this. It's not hard, but like I said, you must be able to identify when resistors are in series and when resistors are in parallel. Now this circuit was a little more complex compared to the circuits we had in part 1, but I think it was very possible that you were able to solve this problem once you had a good understanding of resistors in series and resistors in parallel. Let's work a few more examples. So let's do this one, right? It says find the equivalent resistance RAB in the circuit. So we know we're going to be looking through these terminals A and B. So normally we're going to start from the wires furthest away from the terminals A and B, right? Which is going to be more so on this side. Now when we look at this problem, it's a little different from what we're used to seeing, right? Believe it or not, it is. Now we must be able to have a good understanding of what's happening here, right? So think about it like this. This is the positive terminal. This is the negative terminal. Current is going to enter the positive terminal, right? It's going to leave. It's going to come this way. So this is the current. The current is coming that way, right? Once the current reaches this node right here, guess what's going to happen? That current is going to split. So now the current has two options. It can go this way and it can go this way. Once the current reaches this node right here, it has options once again, right? So now this current can either go this way or this way. It seems like a lot of ways this current can go, right? Now think about it. Once the current starts to travel this way, right? And it reaches this node, it has two options once again. It can go this way or it can go this way. Do you see all of that? What does that mean? That means these resistors in this branch is parallel with this resistor in this branch, right? So once this current travels to this node right here and it splits, that means these two resistors are going to be in parallel. Once the current reaches here, we know these two resistors are also in parallel. Now you might be wondering, what was the point of labeling the currents and the nodes? Well, I want us to be very, very careful, right? I want us to have a good understanding intuitively of what's happening here. So a current is going to come in this node right here. It's going to enter this node and it's going to split, right? Some of the current is going to come this way and some of the current is going to go this way. Now, because there is no resistor right here, we cannot say that these two are in parallel, right? We cannot say that. But just imagine once this current enters this node right here, right, which is the same node, we know that the current is then going to split again. So this current, once it enters this node, has two options. It can go this way and it can go that way. Therefore, we know that these two resistors are going to be in parallel, right? We know that because the current that enters this node is going to be the same current that's going to be supplying this 4 kilo ohm and this 2 kilo ohm. Now, as the current in the 2K is coming over, right? We know once it enters this node, it's going to either go this way or that way, which means this current that enters the node is going to form parallel resistors which means once the current splits, and because the current is going to split, we know that these two resistors are in parallel. So that's just the basics behind all of that. I mean, that's the way I like to look at it, right? For the most part. You don't have to label these things, but at least try to have an understanding of it, right? That's kind of what I want to teach. I want you to have a good understanding of what we're about to do. Because these types of problems, once they get like this, it can be a little confusing, but I don't want you to get confused, right? So the first thing I'm going to do is I'm going to start further away from the terminals A and B. So I'm going to start right here at these two resistors, right? When I look at this, I can see that these two resistors are going to be in parallel, right? And because they're in parallel, I can just find the equivalent resistance. So when I find the equivalent resistance of that, that's going to give me 12 times 6 over 12 plus 6. That's going to give me 72 over 18. Therefore, the equivalent resistance is going to be 4 K ohm. So let's redraw this now. We're going to have 12 here, 12K. This resistor is going to be 2K. Now we just found the parallel equivalent resistance of these two, which is going to be 4 kilo ohm. So we got 4 kilo ohm, right, for these two resistors. Now this resistor here is going to be 4 kilo ohm. So we have 4 kilo ohm. Okay. Now when we look at this, we know these two resistors are now going to be in series, right? So because these two resistors are in series, we're just going to add them. We can redraw this to look like so 2K plus 4K is going to give us 6K. Now when we look at this, we have options, right? We can look at this and see that all three of these are actually in parallel. If you notice, right? These three resistors are going to be in parallel. Now if you can't see that, let's just do it one step at a time, right? Now when I look at this, I know these two resistors are going to be in parallel. And we know that because when the current enters this node here, it's going to split. It's going to go this way. It's going to go that way. Now, once this same current right here enters this node, it's going to split again. It's going to go this way, and it's going to go that way, which means these two resistors are going to be in parallel. So when we solve for this, we're going to have 4 times 6 over 4 plus 6. That's going to give us 2.4 kilo ohm. So let's redraw this circuit. We know this is going to be the 12K resistor. And we just found the parallel resistance of these two resistors, which is going to be 2.4 kilo ohm. Once again, these resistors are in parallel. So we can say 2.4 over 12 plus 2.4. That's going to give us 28.8 over 14.4. Therefore, the equivalent resistance is going to equal 2 kilo ohm. So this is going to be our answer for this particular problem. Let me just redraw it one more time. So we're going to have A, terminal A, terminal B, and this is going to be 2 kilo ohm. Therefore, our answer for the equivalent resistance looking into terminals A and B, is going to be 2 kilo ohm. So this is how you solve a problem like this. It's not hard, right? But once again, like I keep saying, you must be able to identify when resistance are in series and parallel. The way I like to go about it sometimes, especially with problems like this that can get a little tricky, is I like to follow the convention of the current, right? If I know a current is going to flow into a node, and then that current is going to split into 2 directions, I know those resistors in both of those directions are going to be in parallel. And that's how I'm able to solve most of these questions. Like I said, they aren't hard, but you must be able to identify when resistors are in series and when resistors are in parallel. And the easiest way to do that, for me, is going to be just to identify where the current is flowing in that particular circuit. Let's do one more example. This is our final example. Let's do this one. So it's the same exact question. Find the equivalent resistance, or looking through terminals A and B in the circuit, right? Now this circuit diagram looks very similar to the one we did up here. But notice, in this particular circuit, we had a resistor in this wire. In this particular circuit, there is no resistor in this wire. So let's see if that makes a difference, right? Now the first thing I'm going to do is I'm going to look to see where terminals A and B are. Well, these are going to be terminals A and B. So I'm going to start, for the most part, furthest away from terminals A and B, which is going to be this side here. Now when I look at this, it's something interesting is going to happen, right? But before I do anything, let's just look at the direction of the current, right? So we're going to go this way. Remember, this is the positive terminal for A, negative terminal for B. Current's going to enter, right? When current enters this node here, it has 2 options. Some is going to go this way, and some is going to come this way. You see that? So current has an option. It can flow this way through this 6K resistor, and then some can flow this way. Now once it flows this way, you have a problem, right? And that problem is the current is then going to split again. Now once the current flows this way, the current is then going to split again. Let me use a different color. So that current, which enters this node here, is now going to go this way or this way. Do you see that? So this current right here, once it enters this essential node, is either going to go this way or this way. So as we look at this now, we say to ourselves, well, what do we do at this point? Well, once again, we have to be able to understand the flow of current, right? So this current is now going to come this way. Now when it gets right here, I'm going to change the colors one last time. So this current is going to continue this way, and it's going to enter this node right here. Now once it enters this node, you would think this current has 2 options, right? You would think this current has an option to go this way, an option to go that way. And the thing is, the current does have 2 options. But you must be able to understand this circuit, right? Understand it. Remember this. Current is always going to flow through the path of least resistance. Always. So once the current enters this node right here, right? It can go either this way or it can go this way. Because there is no resistors here, all of the current that enters this node is only going to flow in this direction here. So it's only going to flow this way, right? Do you see that? Very ironic, right? It's only going to flow this way. So I want us to be able to recognize that. Now, once you can recognize that, you would know that even if this current comes all the way around here and enters this node, it's not going to flow this way because this has a resistor. It's always going to take the path of least resistance. So even though this current is flowing through this 6K resistor, once it reaches this node, it's just going to come straight down. It's not going to go this way. Therefore, we can say that this 2K resistor essentially is non-important, right? For this particular problem, finding the equivalent resistance, we don't even need to have this 2K. Essentially, this is going to be shorted, right? It's not going to be there. So we can actually redraw this circuit without this 2K resistor here. That's one way to look at it, right? Another way you can look at this problem is you can say, you know what? Even though there isn't any resistor here, we can draw in an imaginary resistor. So let me redraw this, right? And I'm just going to draw it with an imaginary resistor. I'm going to solve it like that, and then I'm going to go back to explaining what I was explaining before. Just remember, everything I set up here was for you to try to understand and remember. Current is always going to flow through the path of least resistance. In this particular problem, the current had a choice between going between the 12K and the 6K. So it's going to split. Of course, more current is going to flow through the 6K than the 12K because current always takes the path of least resistance. But in this particular situation, there is no resistor here. So once the current reaches here, why would it ever want to go this way? It's only going to go this way, which means this is going to be short-circuited, right? Try to understand that. Rewind it a few times if you need to. But let's now redraw this, right? And I'm going to redraw the same circuit diagram. And in this branch, I'm going to add a resistor. But the value of that resistor is going to be 0 ohm. So let's do that, right? I'm going to redraw it. So now for this branch, I'm just going to put a resistor there. And I know that's going to be 0 ohm. So the first resistor I'm going to label is going to be the resistor we just drew in, 0 ohm. Now the resistor at top is going to be 6K. The resistor to the left is going to be 6K. The resistor to the right is 2K. And the resistor to the bottom left is 6K. We know this is terminal A, this is terminal B. Okay? Now if you want to, you can draw in a resistor right here. But I'm not going to do it, right? You can do it here if you like to. The reason is because it's at the end and not in the middle, I know this isn't going to really affect me. But I just drew this one here so you can kind of have a good understanding of why this is going to be short, right? So let's look at this, right? We know a current is going to flow in this direction, right? We know current is going to come in this direction. That's what we're assuming. We're assuming current is coming in this direction here. Once it reaches this node, we know it's going to split and go between either the 0K or the 2K, right? So for example, we know that. And because it's going to split, we can say that these two resistors are what you say is parallel, correct? So when we solve for that, we can say 2 times 0 is going to give us 2 plus 0. That's 0 over 2. Now we know 0 divided by 2 is just going to give us 0 ohm. Therefore, essentially, these two resistors that are actually in parallel is going to be 0. So because these two resistors that are in parallel equal 0, we know that we don't have to include this 2K ohm resistor when finding the equivalent resistance looking from the terminals A and B. Just like I said earlier, imagine this, right? If you look at this circuit, when the current enters this node, this resistor is going to be shorted because the current is always going to flow through the path of least resistance. So essentially, we wouldn't even have this resistor here. So let's redraw the circuit once again. We just found the equivalent resistance of these two resistors. So we're going to have A and B. This top resistor is going to be 6K. This resistor is going to be 6K. And this resistor is going to be 6K. Now, if you look at this, you can see all three of these resistors are in parallel. But if you cannot see that, let's just go step by step, right? We can say the current is going to enter this way. Once it enters this way, then we know for sure it's going to split here. So some is going to come here, some is going to come here. Then the current is going to enter this node, and then it's going to split once again. So some is going to come here, some is going to come here. So when we start to do this now, we can say these two resistors are in parallel because the current coming in this way has two ways it can split. So we can say 6 over 6, 6 plus 6, and that's going to give us 3k ohm. So let's redraw this one more time. We're going to have 6k up here, and the equivalent resistance is going to be of those two resistors 3 kilo ohm. We know these two resistors are in parallel because once the current enters here, it's going to split. It's going to come this way and it's going to go that way. So therefore, we know these two resistors are in parallel. So when we solve for this, we're going to have 6 times 3, 6 plus 3, which is going to give us 2 kilo ohm. So when we redraw this circuit for the final time, it's going to look like this. Therefore, the equivalent resistance, looking through the terminals A and B, is going to be 2 kilo ohm. This is going to be our answer for that problem. Okay, so we've successfully solved 3 different problems. Like I said, these problems are very simple once we know when resistors are in series and parallel. But it's also important for us to be able to look at a circuit and follow what's going on in that particular circuit, right? So in this case, we know we're going to have a short in this resistor right away because we have a wire with no resistor through it, which means right away we could have just threw this resistor away and automatically redrew this circuit diagram to look like this. We could have said, and of course we have the terminals A and B, right? But right away we could have just drew it to look like that and we would have been able to solve our answer. But it's important for us to be able to look at these particular circuit diagrams and try to follow what's happening there, right? A good rule of thumb is if you have a wire like this that's in between or inside of the circuit, even on the outside of the circuit, you can always add in a resistor of 0 ohms and then still solve it the way you normally would because you would know whether resistors are in series or whether resistors are in parallel. And once you do that, you will still be able to find out the correct answer. So there are multiple ways you can solve these problems. It's really up to you. I want to give you a variety of ways, right? Because one way you see it in one problem, you may not really see it that way in a different problem. Once you have an intuitive idea of what's happening, right, you will always be able to be on the right track to solve these types of problems. If you have any questions, please leave them down below and I'll be sure to get back to you as soon as possible.